Well, listen, I wanted to just get you on board with where we are. Our next exam today is the 19th, so we're here. And our next exam, what's on Monday? Oh wait, that's fall break. Yeah, it's on November 2nd. Yeah, we have fall break on Monday. Did y'all know that? Monday and Tuesday, in fact, we'll be out. And so we'll have Friday, Wednesday, Friday, and then Monday. So 4 more class days after today. So what that means for your exam is that we'll have chapter 5, 6, and 7. All 3 of those are pretty short chapters. And then on the 4th exam, it'll be chapters 8, 9, and 10, which are also, 8 is kind of the longest chapter, but 9 and 10 are not that long, and they're also stuff that you've probably seen in chemistry. You know, ideal gas law, calorimetry, stuff like that. Okay? So, for now, we're going to wrap up chapter 6 today, and we'll do some more practice for chapter 6 for the momentum things. And we'll move into chapter 7, maybe at the end of today, or maybe on Friday. Any questions about where we're headed, what we're doing? Yeah, on Wednesday, November 2nd. Yeah, I was just trying to mislead you and fool you and think it was on. So it's on the 2nd, November 2nd. All right. Okay. Any other questions, Joe? Feel comfortable with that? I don't want to say it's an easy exam, but it's probably, of the 4, it's probably the easiest exam. But not easy, just easier than the previous exam. Okay? Okay, let's look at some different kinds of collisions. This came up in your homework, which is due on Friday night at midnight. There are 2 types of collisions, elastic and inelastic. And you know, in all collisions, momentum is conserved. In all collisions, the initial momentum is equal to the final momentum. In every collision that has ever occurred or that ever will occur, momentum will be conserved. However, only in special collisions is energy conserved. And we call those collisions elastic collisions. An elastic collision is one where both momentum and energy are conserved. Ooh, sorry. When the 2 objects collide and they bounce off of one another and they lose no energy. The way that you lose energy, like if you have a car crash or something that, you know, crashes into something, is it produces all sorts of energy that's lost. Things like sound, heat. In a car crash, most of your energy goes into deforming the car, right? That it'll crunch the bumper, it'll crunch the fender, and that most of your energy goes into that. Which, by the way, is why, you know, newer cars anyway have not real stout bumpers like they used to have, but they have bumpers that are made to collapse. They're made out of things that will collapse. What are some examples of collisions in which energy is conserved? What type of forces conserve energy? Well, let's think. We talked about conservative and non-conservative forces back in the previous chapter. There were really only 2 forces. Well, there were 4, but really only 2 that we're concerned about, forces that conserve energy. And one of them is gravity. And what's the other? The electric force, right. Non-contact forces are field forces. So a field force is where the objects, they don't actually come into contact with one another. So if you have 2 charged objects that are moving towards one another, they'll collide, but they'll never actually touch. They'll interact with one another, but they never actually touch. And so those are really the only true elastic collisions. I think you had a quiz question about that. Is that true? Yes, the only true elastic collision is when you have 2 particles that are charged, like atoms or molecules that come together, and they don't touch. So the examples include, well, atomic collisions, and that's really about it. Atomic or molecular collisions. But anytime you have field forces at work. In play or at work. Anytime your field forces are at work in the collision. We can also approximate some collisions of elastic. You know, I was talking about earlier, I think of elastic as an elastic collision. When I think of the word elastic, I think of something that's really bouncy, right? Like if you have a really good tennis ball and you drop it, it'll go down and it comes up pretty close to where you dropped it from. Am I right? I don't play tennis, but I think that's true. Is that right? A good tennis ball, if you drop it, it'll go down and it'll come back up almost to your hand. What's that, Chandra? A volleyball does that too. Now, in that, if it comes all the way back up to where you left it, then from where you dropped it, that means that it's lost no energy, or very little energy. So elastic energy, I think that, well, that's bouncy. Bouncy things don't lose much energy. On the other hand, if you have a really old tennis ball that's not very bouncy, that's not very elastic, you drop it, what does it do? It just stays down on the ground. It just doesn't bounce very much at all. And so in those, energy is not conserved. We do approximate some collisions as elastic, such as like billiard balls. For example, you can probably think of some others where they lose energy, but they don't lose much energy. Usually it's things like this bouncing off of one another, where they're really hard so they don't deform. And so if you have two billiard balls that bounce off of one another, the only thing that they really lose is, you know, what? Sound. They lose a little bit of sound, which isn't really that much energy anyway. Okay? So elastic collisions conserve energy and momentum. In inelastic collisions, only what is conserved? Only momentum. Every collision in the universe conserves momentum, even if you have non-conservative forces at work. Energy, however, is not conserved, because you have to have conservative forces at work. And as I said, these are most collisions in the universe. Everything but those molecules interacting with electric field forces. Hold on a second. Okay, we also have a type of collision called perfectly inelastic. So remember, inelastic means only momentum is conserved. And I don't know why it's called perfect, but when I say perfectly inelastic, all that means is that the objects stick together. You had a couple of problems, at least one on your quiz that's due on Friday, where you have perfectly inelastic collisions, where you have two objects that come towards one another, or maybe one object that comes towards a stationary object, and they stick together, and then they move off in the same direction, stuck together at the same speed. That is a perfectly inelastic collision. You work it in exactly the same way as we've been working these other problems, these conservation of momentum problems. The only difference is that it's a little bit easier, because at the end, your two objects stick together, and so they both have the same velocity. So they both have the same final velocity. And here, as I said, momentum is conserved. Energy is not conserved. So let's look at this. If I were to do this problem, let's just do it algebraically with no numbers, and then we'll work through one with numbers. Here, I would say that P initial is equal to P final. P initial would be M1 times V1I plus M2 times V2I. Recognizing, and often in the problems, I'm not going to give this a negative value, but recognizing that as it's drawn, V2I must be a negative value. And this is going to equal to M1 plus M2 times the final velocity. And both of those will have the same final velocity. Because they're stuck together, they're going to move in the same direction. Well, by the way, since we're talking about collisions, out in the quad at 3 o'clock, they're going to have some of those big bouncy balls that you put over your body. Y'all know what I'm talking about? And then you run up next to one another, and you can collide. Momentum is conserved in those collisions, too. Seriously. Oh, you'll be in last. It's 3 to 5, I think. Anybody going? It's really happening. There's a poster on the bulletin board. Don't you read those things? The bulletin board? Today at 3 o'clock. All right. Let's see. Let's work through problem. Or actually, let me just recap because that's the end of the chapter, and then we'll go. Wait, don't move it. Just let's recap. I'm gonna sort of recap the whole chapter. It's not a real long chapter. We can do it in just a few lines, and then we'll go back and we'll work some practice problems. So in this chapter, we really have two classes of problems. We have the problem that involves Newton's second law. F is equal to delta P over delta T. Remembering that these are both vector quantities, so we have to take into consideration the directions of all the various speeds. This was like the problem of a car running into a wall, or a tree as it may be, and then bouncing off of it. Or also we did the pedestrian test dummy, where we could sort of estimate the force that acted on his knee. Generally, you'll be able to define these or identify these problems because they'll just have one object, like a truck. Or they'll have, just one object that is in motion. The other type of problem is the conservation of momentum problem. That is that PI is equal to PF, where I take the initial momentum and set that equal to the final momentum. You also need to know I might ask you, hey, what is the momentum of this object that's moving with a certain speed? And you would just say, well, gosh, P is equal to M times V. So as far as calculations, that's really all that we got. We just have Newton's second law and the conservation of momentum. And we'll work through some more of these now in just a second. We also had some other things, like you need to know elastic versus inelastic. Excuse me. You don't really need to know what a perfectly inelastic problem thing is, but you need to know how to work a problem that's perfectly inelastic. That's it in this chapter, actually. Just 4 little lines. Okay? You want to work through some practice problems? See how you do on them? Let's go back to the back, and we'll look at some of those old tests in the back of your book. Looks like exam 3. Some of these are involving conservation of energy. Let's look first at number 11 on exam 3, where we have this perfectly inelastic collision. And I want to know what is the final velocity of that object, number 11. What is the final velocity of these objects? Right now we're doing number 11. But after this, we're going to do number 10. So if you finish number 11, go ahead and start on number 10. And get a head start on number 10. We'll do about, 20 or 30 more seconds here on number 11. Stop at 150, y'all. 150. 15 more seconds. Just 5 more seconds, so just guess if you're not sure. A few more seconds. Okay, good. Let's see. I'm pretty sure C is right. You got to be careful with your signs on these problems. That's where students are going to mess up, are the signs. So I do my initial momentum here, and it'll equal to my final momentum. My initial momentum is this times this. That's 2 times 4, plus 4 times -3. Because notice this is moving in the negative direction. And then that's going to equal to 2 plus 4. That's the total mass of this times VF. So that's 8 minus 12. That's what, -4 divided by 6. Wait, that's not right.
That's D.
Yeah, so D is right. It should be, but I'm asking for the magnitude of the final velocity. Yeah, so VF is equal to 8 minus 12 is -4 over 6, which is D. Let's see, what did y'all do for C? That's what you did, yeah. So that's why you messed up here on C, is that you didn't include the sign here. But look, just be prepared for that, because I'm just going to give you the magnitude of the speed. I might tell you to the left or the right, or I might give you a figure like this. I will tell you is it to the left or right, or I'll give you a figure like this. But you'll need to determine, well, is that positive or negative? So just go into this test knowing that I really got to think about my signs on this chapter particularly. Okay, so D is the right answer here. Y'all go ahead and do number 10. 10 is a little funny. Like, not ha-ha funny, but, you know, odd funny. So, let me start the thing. Go and put your answer in if you haven't already. This is the same idea behind a rocket, by the way. A rocket throws stuff in that direction to make it go in this direction. Did y'all just share the answer all across the front row? Feel free to ask your neighbor what they threw up there. So let's do about 15 more seconds, stopping at 1:35. Okay, I think that is right. I'm going to go and mark it right. So you might want to approach this problem not just looking for the mass. So similar to the problem that we had before, but looking for the mass instead of the speed. So what I have here is a car with a machine gun on it, and it fires bullets in this direction, causing it and giving it a velocity in this direction. Now, initially, it's not firing any bullets. What is the momentum of the car? It has 0 momentum. So my initial momentum is 0. And the final momentum has 2 parts. It has the momentum of the car, and it has the momentum of the bullets. And I know that these have to add up to equal to 0 because momentum is conserved. And so if my initial momentum was 0, my final momentum has to also be 0. Because momentum is conserved, these two momenta have to be the same. Momentum at the top, momentum at the bottom, they have to equal 0. So that tells me that these two, since they have to add up to equal to 0, have to be equal but opposite. So the momentum of the car has to equal the momentum of the bullets. So I can find the momentum of the car. Let me write that. So the momentum of the car has to equal the momentum of the bullets. And the momentum of the car is also equal to the mass of the car, which is this, times the speed of the car, which is this. And that's what? 3.125 times 10 to the 4. Is that right? Yeah, that's right. Kilogram meters per second. That is the momentum of the car. You know, with me, what I did is I said this number times this number gives me 3.125 times 10 to the 4. Now, that has to equal the momentum of the bullets. So I'm going to say 3.125 times 10 to the 4 equals the mass of the bullets times the speed of the bullets. I know the speed. It was 250. So I divide both sides by 250. And I get the total mass of all of the bullets that are fired. And what does that give me? Anybody? 12.5? Is that right? 125? That sounds more reasonable. Kilograms. That's equal to the total mass of all of my bullets. But now I want to go back and look. What is it asking for? I'm asking for how many bullets are there? And each bullet has a mass of 0.025 kilograms. Oh, that's where you're getting at. So I divide this by 0.025 kilograms in order to give me the number of bullets. And that'll be, was it 5,000? And that's equal to 5,000. So that last little part was a little bit different. But the first part is I find the total mass of the bullets. Because I say my momentum is conserved. And then I just said, well, these two have to be equal because they add up to equal 0. And so I find the momentum of the car, because I know its mass and velocity, and set that equal to the mass and velocity of the bullets. But recognizing that this is the total mass of the bullets. Okay? That might have been, yeah, sorry.
So how did you know the initial momentum was 0?
Oh, the initial momentum is 0 because the car is not moving and the bullets aren't moving. So if I have something that's stationary, the initial momentum will be 0. You had a similar problem, we'll see one in the concept test soon, where you have a system that's stationary and one thing goes off in one direction and one thing goes off in another direction. It works in a similar way as this. That answer your question? That's a good question. Okay? Let's do one more and then we'll do some more concept tests. Finish off the concept test for this chapter. Any particular questions? Or you want me to just pick one? All right, let's do 13 because 13 is going to be a different type of problem. Number 13. You should be able to read this problem and figure out, is it a conservation of momentum problem or is it a Newton's second law problem? Many of you are getting the right answer, but about a third of you have the wrong answer. So why don't you ask around if you've gotten an answer and see what your neighbors have put. Oh wait. Okay, doing pretty well. I'm going to stop at about 2:15 or 2:15. Well, doing okay. Well, no, we're not doing that well at all. So why don't we just step back for a second. So many of you have said it is either B or D. And in fact, you're about split even. About B or D. I want you to think about the signs of the velocity very carefully. And then maybe rethink your answer because, you know, half you're right, half you're wrong. It is either B or D. But I want you to think carefully about the signs, particularly of your velocity. Because since momentum is a vector quantity, you have to include those directions. All right, I'm going to stop at 3:15. 3:15. Okay, it is B. Very good. Listen, anytime you have one of these problems, and you're right to think that this is a Newton's second law problem, F equals delta P over delta T, and I want to know what is this force. You know, a couple things keep me off that it is a Newton's second law. First, it's just asking for the force. And so if it's asking for the force, I know it has to be this. Also, there's just one object that's being involved. It has an initial and a final velocity. So I'm going to be looking at my Newton's second law. And then also, this is mvf minus vi divided by delta t. M is not changing, so the delta just applies to the velocity, not to the mass. Though remember, mass can change too. And my VF, this is where many of you are making a mistake because you were putting D when really the answer was B, is that you are getting your signs incorrect. Now you're right to say that VF equals 4.2, but you were saying that VI was equal to 4.5, when in fact VI is negative 4.5. So imagine I have this ball, it's going down with VI, and then it bounces up, and it has VF. And so that's going to be a negative value. So that's going to work out, VI will be negative because it's down. So my mass is 0.3 kilograms, VF is 4.2, minus negative 4.5, divided by my time, which is 0.03 seconds, and that gives me 87. Listen, if you encounter a problem like this, just remember that this is always going to be the case. If I have an object going one direction and coming back the other direction, it's always, even though it's a difference, it's going to be a positive in that, because one of them will be going the opposite direction. Okay? Just remember that. If they switch directions, I'm going to have a positive. If we're on this test, you want to think your signs, that you're getting your signs right. Like that song. You could do that song, right? Y'all know the song? Signs, signs, everywhere the signs. Y'all know that song? Y'all don't know that song? Seriously? I think it was Black Crows or somebody. Was it Black Crows? Okay. Let's finish up our concept test. I don't think we had finished it yet, had we? Which one were we on? Do you know, Caitlin? Okay, 6.12a we answered. We did answer this one. And remember, this is a perfectly inelastic collision because they stick together. We just have a few more. Here I have a uranium nucleus at rest. Oh, and by the way, it's at rest, so initially I have zero momentum. The two split up, they undergo fission, and they split into two fragments. One's heavy and one's light. Which fragment has the greater momentum? I'm going to stop at 50. 50. Yeah, you're awesome. C is the right answer. Because if he has zero momentum here, that means he's also going to have zero momentum here. So whatever momentum here, which is positive, is going to equal whatever momentum here, which is negative. They will have the same momentum, but in opposite directions. Okay? Zero momentum, zero momentum. Just like that problem we did. What was the problem? The machine gun on the platform. Just like that right here. Let's see. Why could the astronaut not? Why was he not able to book a room at the hotel on the moon? Why? It was full. The moon was full. The uranium nucleus at rest undergoes fission, same as we had before. Which fragment has the greater speed? We've already said they have the same momentum. Which has the greater speed, or do they both have the same speed? All right, I'll stop at 40. Stopping at 40. Okay, awesome. B is right. They have the same momentum. Momentum is mass times velocity. So the smaller one, which has a smaller m, will have a bigger v. Hey, do y'all know what the speed of time is? Do you? 1 second per second. That's the speed of time. 1 second per second. Is that not funny? I thought that was kind of funny. Okay, Amy and Gwen are standing on slippery ice and they push off of one another. Amy slides at 6 meters per second. What speed does Gwen have? I always get these mixed up. Amy is the one in blue. So this is Amy, and then this is Gwen. And we want to know what speed does Gwen have? We'll stop at 1 minute. 1 minute. One minute. Okay, good. E is right. This is a lot like the railroad car problem. I start out with an initial momentum equal to 0. And then in the final state, my final momentum will be the momentum of Amy plus the momentum of Gwen since one of them has to be negative, but they have to be equal but opposite because they're going to also equal to 0, they'll both have the same momentum. And so if Amy slides at 6 meters per second, she has 3 times the mass of Gwen. That means that Gwen is going to go faster by a factor of 3. So this was 6. She's going to be going at 18. Is that what y'all put? Yeah, E is the right answer. Okay, let's try this one. Very similar. All right, we'll stop at 105, 105, or we'll go, yeah, 105, 5 more seconds. Okay, B is right, I think. So when I fire the cannonball, the momentum of the cannonball will equal to the momentum of the car. They're going to be equal but opposite, so I can just set them equal. I'll say the mass of the cannonball times the velocity of the cannonball is equal to the mass of the car times the velocity of the car, or the speed of the car, really. The mass of the cannonball is 10, velocity is 50, mass of the car is 1,000. So V of the car has to be a half meter per second to the right. So B is the right answer there. And go down from here. When a bullet is fired from a gun, the bullet and the gun have equal and opposite momentum. Just like with that, right? With the previous problem, you have a bullet going in one direction, the gun is going to go in the opposite direction of the rifle. So why then is the bullet deadly, whereas it's safe to hold the gun, which has all this momentum? Why is it safe to hold the gun? What's the difference between the bullet and the gun? It's not sharper, that's not it. The answer is not A, okay? What's that? Right. I'm going to stop at 110. 110. Okay, good. C is right. The momenta of these are equal. The bullet and the gun, the product of their mass and velocity, are both equal for the bullet and the gun because they have equal momenta on each side. However, the bullet has a small mass and a big velocity, whereas the gun has a big mass and a small velocity. And actually, we had considered not only the gun, but the person holding the gun, right? Because you move with the gun when you shoot it. So because kinetic energy, as you all know, is 1/2 mv squared, if I increase v by a lot, which I do for the bullet has a much bigger speed than the gun, then it's going to have a lot more energy than the gun because I have this quadratic factor. So if I double the speed, I quadruple the energy, for example. All right. let's spend some more time practicing. Either that or we can move on into chapter 7. What would y'all rather do? Practice, that's what I thought. So let's just spend some more time practicing. We'll look at chapter 5 stuff too. I think some of you still need a little work on that. Let's look at some chapter 5 stuff. Remember, chapter 5 was largely conservation of energy and the work energy theorem. So let's start with this number 2. You are going to have a problem like this. That'll be similar to number 2 on the old exam. I have this cart that moves along a track, and I want to know the speed of the cart at point B. Let me zoom in for y'all. The speed of the cart at point B. If you finish number 2, go on to number 3, because we'll do it next. Finish number 2, go on to number 3. Remember, on these, you're asking, what is the energy at some point? Does it have kinetic or potential energy or both? And then you're comparing the energy at one point to another point, because the energy at all points in this system are going to be the same. Finish 2, go on to number 3. We'll do that next. Okay, we're a little split up on the answer, on what the answer is. So, feel free to ask your neighbor what they put if they got something different. Talk about it. I do want to remind you that I do have a speed up here, that the object is traveling at a certain speed. It's at 4 meters per second. What's up, guys? Can y'all see okay? You okay? All right. All right, I'm going to stop in about 15 seconds, 2:40, say. It's good. If you can work this in under 3 minutes, that's a good goal to shoot for, okay? 2:40. Okay, I'm pretty sure A is right. Let me show you. So you want to take your energy here, because I know the height and I know the speed, and then I'll set it equal to the energy there. Now here I have both potential energy and kinetic energy. And down here, I only have kinetic energy. I have potential energy here because I'm at a height bigger than 0. And I have kinetic energy because my speed is more than 0, 4. Down here, I don't have potential because h is equal to 0. So on these problems, you ask yourself the question, is the speed 0? If it is, no kinetic energy. Is the height 0? If it is, no potential energy. And then we set those two equal. I say mgh. I'm going to go ahead and put in 10 meters for that, plus 1/2 mv squared. I'm going to go ahead and put in 4 meters per second squared, equals to 1/2 mv squared. And this is the v that I want to know. Noticing that my masses all cancel. I don't know the mass, so I don't need it. I get 100 plus 1/2 of 16 is 8. I double that, because I have to get rid of this half right here. That's equal to v squared, and then I take the square root of that. So that's 216, the square root of 216. Okay, so it's A. All right? You shall have a problem like that, no doubt. Let's try problem number 3 now. Now at point E, it says it comes to rest. What is the height at which it comes to rest? All right, we're going to stop at 135. 135. 135. Just guess if you don't know. All right, E is right. Same as we did before. We say the kinetic energy plus the potential energy at the very beginning is equal to the potential energy at the end, because at the end it's not moving. This is going to be 1/2 m times 4 squared. I think that was the speed, yeah, 4 meters per second, plus m times g times 10. That's the height at the very first spot, equal to m times g times h, which is what we want to know. M's cancel. This is 108 divided by g equals h. That's 10.8 or 11. So E is the right answer. Okay. Notice that you could have also worked it a little bit differently. You could have said that the energy here, which is 1/2 mv squared. Now we know B, if you trust your answer here, you say 1/2 mv squared is equal to mgh. That might make it a little easier, but you know, if you got that V wrong, then it would get the next one wrong too. Yeah. Go down, sure. All right, let's do one more and then we'll wrap it up. Y'all good on these? Let's look at a different type. Can I go away from here? All right. Let's try number 1. Something that you should know how to do, but we haven't done it explicitly. Number 1. It takes 100 meters to stop a car moving at 25 meters per second. The distance required to stop the same car moving at 50 meters per second under the same conditions is what? Think about it. What I've written up here is the work energy theorem. The work done is force times displacement. The energy that you're taking away is all kinetic energy. I will stop at 135. 135. All right, let's see. So most of you put E. Let's see if that's right. Now you could make this into a calculation where you have to figure out what is F. You could do that, or you could look at it and you could say, well, it took 100 meters to stop moving at 25 meters per second. What happens if I double P? What is going to happen to D? If I double P, I have 2 squared. I'm going to quadruple my D. And D was originally, what was it, 100? So now the answer is going to be E, 400. Is that the way y'all did it? Or did you actually calculate what F was supposed to be? Well, let's see. You could calculate F. Is that right? Well, no, you don't know the math, so you can't calculate that. Okay? I will stop there, y'all. Y'all have a great day. Next time we're going to start chapter 7, so y'all need to be good with 5 and 6. Chapter 7 will be a little bit of a review.